Okay, so it's now recording, and we're gonna this. Okay, right. And so I already have. Oh, sorry. I already have the computer on. Okay, so I already have you guys can see it. I already have the code that we had before. So I'm just gonna pick up from there. So this was called, I believe, Perceptron, right? So Perceptron, click on it. So here we are. So I'm gonna just, we're gonna talk about where we were and then pick up from there. So if you remember, we had some libraries, right? We have NumPy basically and sklearn. We were defining the fit function. So this is kind of what we have to finish. Okay, we did the activation function. We have the predict function over here. We also need to complete the accuracy. And then we had the data set X and Y, the train and test set, and we haven't run all of it. So I'll kind of start at the beginning, right? So we have here creating the data sets. So remember, we're using data sets from sklearn. So we create 150 samples, 2 features, right? And some classes. So this gives us the X and the Y. Then I'm gonna make sure that this is running. So I'm just gonna do clear out right here. Okay. So that's the library. Then I'm gonna go to the data set here, X and Y. I'm gonna run it. Okay. I'm gonna print the shapes. There we go, 150 samples and 2 features. And then we had 150 labels, basically. Okay, so we want to train this model using a perceptron. We do the train test split over here. Okay, and we are basically ready. We have our X train and Y train, and we have our X test and Y test, right, with a 20% split. So now the question is, we need to train the model. Okay, so we're going to give it X train and Y train, and I created a function called fit, which returns weights and biases. Why do we do it this way and not just return the predicted value? Because this paradigm of transfer learning, right? And this idea that you can all build a model with the same architecture, the exact same architecture, and then just one of you trains it. And then once you train it, what do? You share your weights or your parameters with everyone else, and everyone else can just load those weights and those parameters into their own models without having to do the training, and it works. Do you guys see that? This is very important because you may not have all that data or the computing power, right? So this is what happens nowadays when Google or Facebook train huge models on their own data sets, and they share the weights, and then everyone can build their own model. Do you see that? But it does require that we have the correct architecture, right? But everything is built that way, around that way, sharing. So that's another thing for your term project. When you build your models, you can upload them somewhere and say, hey, here's my model. Go ahead and use it. We trained it already, right? These are called pre-trained models, right? It's a very common practice. All right, so this is then the idea why we do the fit and we return the weights and the biases, just so that then these weights and biases become a commodity or something that can be moved around. As you can see now, these weights and biases are added to the predict function over here, right? That's the value of it. And then we're just going to make predictions and do it. So we're kind of stuck here at this moment, right, where we have to do the fit function. We have to understand the training process, what it's called a training. So we're going to go there. If I run this right now, it'll probably break because we hadn't finished it yet. Yeah, so it gives us an error. It says fit is not defined. Oh, and also, well, actually, I didn't run the fit function. So let me. Okay, no error. It doesn't return anything, so it's not going to do anything. The activation was done. We had done this in a previous class. Predict, we can load it in memory. Accuracy doesn't do anything. Load the data set again. Just want to see what error specifically it gives me. No error. Oh, error. There we go. All right, so good. So it returned a non-type object, so it has nothing in the return, right? Okay, so let's go over to the training now. And this is basically it's probably good to keeps doing this. I don't know why it's doing it. All right, so it's probably good not to hard code values. So we definitely need for the architecture the number of samples, right? The number of rows, and then the number of features, which is so n samples and n features. We can get that from X shape. Okay, so that should be good. Right, then what do? We initialize the weights, right? How many weights do we need? We need a weight for every X that we have. So in this case, NP zeros equal 2. In general, you don't want to initialize your weights to zeros. Yeah, you don't want to initialize your weights to zeros, okay, or ones. Instead, you want to initialize them at least randomly. And this is something else that in your project you will have to do. So you get the weights and the biases. But here we're kind of doing everything very from scratch. All right, and then 2 for loops. Remember that? The two for loops are because we do 1,000 epochs, which means we're going to give every epoch. Yeah, so we have 2 for loops. So we have 1,000 epochs, and every epoch we're going to give the entire data set. We're going to give the entire data set to the model. Okay. So then we do 4, this symbol just means that we're discarding the index, although you can use it for I and, I or J in range of 1,000, right? And that iteration, you just set that value. So you'll have to figure out sometimes you have to be careful with picking this value because it might turn out that if you had done 2,000, your model would have been pretty good, right? Sometimes that can be the case. That's why we want to plot. You already have functions to plot losses and everything. We have the enumerate function, which allows us then to iterate through the train set. Here, we're extracting every sample one at a time, but remember, in general, you want to extract them in batches, okay? So that's always a good idea. So the enumerate is very handy because it gives you the index and the value itself, so you can use the index as we did in the example here. So now, if you remember, we do this operation. I did find that code that we had done in class, the dot product, and I loaded it on GitHub. So just to remind you, here, GitHub. right? And I loaded it under the course site. And I just want to bring it up because it's really important, actually. If you go to neural nets, and I created this folder called NN Maths, and it's basically where I'll throw in things that are just like the mathy part. So if you notice, I added this dot product, and I remember we did this before. So I went over how this computation is done, right? And if you look at it in for loops like this, it's so nice because it's very intuitive. It's very easy to understand what's happening, right? And so you have it here like this, and a lot of the time in machine learning, you kind of wish that things were written this way, because if they were written this way, they would be very easy to interpret and understand. But why is it that we don't write things like this? Because it's inefficient, right? It's very slow. And so all the time, what ends up happening is we have to write the linear algebra equivalent of this. And sometimes those which are usually matrix multiplications, become very difficult to see, but they are efficient. Do you see what I'm saying? So there's this trade-off between we understand the concept and it's easy, but unfortunately we can't code it in the for loops like this because it's too slow. So we have to look at it from the other perspective. All right. So anyway, we covered this before, but it allows us to multiply the x and the w's in the vector. So I'm going to go back. Now, instead of doing all of that, we can conveniently use operations that are already built in our library. So all the libraries that we use, either TensorFlow, PyTorch, or NumPy, have basically built-in operations. And this is, in this case, NP dot, the dot product is doing literally what we just saw in that other script, but it just does it very efficiently and fast, okay? So you can see here, we're basically creating the function y equal w times x plus b. So you can see we've got the bias parameter over here. We've got the weights parameter over here, the x parameter. So we're performing that multiplication, and then we get the value, right? The multiplication. Now, in the perceptron, we already talked about this. Remember, it goes through a function, right? The step function, which is still a linear function, but it doesn't make any difference. It just helps us to convert the values to the range that we want from zeros to ones. Remember, these are still linear functions, so they don't have any neural net MLP capabilities, right? So the perceptron obviously cannot solve XOR. All right, but we do run this through the activation, and this will be standard practice in other models, except those models will have more layers than this, okay? All right, so then what we need to do is we need to compare the predicted to the real and do the perceptron update rule. So all neural networks do this, but this is where it starts to differ. And this is what today, this is where stochastic gradient descent comes in, right? How do we update the weights, right? And as you have seen with Keras, you didn't even have to do this, right? Because Keras really manages to abstract all of this, But this is what's happening behind the scenes, basically. Okay, so we want to compare the real to the predicted and do the update. So as you can see, okay, so this is where we stop. We built a little function. You can do this in one line of code, but I just kind of broke it down into several lines of code just so that it's easier to see. So you can see the first thing we do is we take the difference between the predicted value and the real value. Do you agree that this is the real value? So remember, we pass to it the whole vector, but we're just indexing that index, right? With that value of the index. And remember, our function only predicts one value. So you asked me at some point, why, how do we do this in batches? We would have to do the same here. It would be better if we do this in batches, okay? Batches of 16, batches of 32. But currently it's only for one. All right, so once we take the difference between, let's say that we're predicting 1 and it gives you 0, so then that's the difference, right? And then you take that value and multiply it times the learning rate, which we define currently as 0.01, and we're just going with that. And that gives us what we're calling here the update value. Do you guys see that? All right, so once we have the update value, what do we do with that update value? we update the weights and the bias. So in this case, this is the most basic thing that you can do. You just take weights like this. You see that? These are the parameters. This is where we're actually, the network is learning, right? This is what learning means, that the network's weights are being changed, okay? And so we do weights equal the original weights plus, and then now update, and just like that for now. Do you see this? What's important here is, one of the important things is, if you want to think of this in a very simplistic way, sometimes this value could be positive, sometimes this value could be negative. You see that? And the learning rate is 0.01. So effectively what's happening is that sometimes weights are what? Weights minus 0.01, and sometimes weights plus 0.01. So basically that we're increasing them or decreasing them. If you made the value of the learning rate 1, it would be +1 or -1. What's the effect there? It's a big change. What if the value of the learning rate was 0.00000001? Well, minus that very tiny change. Do you see that? And that's why it would take longer for the model to learn if that learning rate is really, big, a lot of zeros. On the other end, you don't want it to be 1 because then it's too broad. Okay, so we do update here. Okay, and then we'll come back and look at other ideas. Once we also want to do that to the bias. So we do bias equal bias, and then the same thing. But sometimes people write minus instead of plus. That's a common thing. Doesn't matter, right? But you can do, it would just have like the opposite effect, right? So, but let's do plus here. And then to the update. And then once you do that, and it's hopefully if you've trained it, then what do you return? The weights and bias. So at this point, we have a function in a very crude way with the perceptron approach that learns. Do you guys see that? Okay, so we're going to run this and just see how it performs. So I'm going to run that. The activation was good. And for predict, so we did the training. So I think that's ready. Activation is ready. Predict was done, right? Because predict just takes the X test data, the learned weights and biases that we have. We do the same dot product operation. We get the linear. It still needs to run through the activation, right? The step function, because that's what tells it to predict zeros and ones. And then we get Y pred. Okay. Now I hit run. And then I haven't done the accuracy yet. We can define this later. But I think we should be able to run it now. So let's see what happens. Should give us weights and biases. It's taking a while because it's doing 1,000 epochs with 150 samples, right? Oh, it finished. Oh, that was fast. Okay. So now what can we do? Well, let's look at the weights. Why not? So what were the weights initially? Zeros, right? Zero. Didn't learn. Okay. Oh, no. All right. So let's look at bias. Zero as well. So did return weights and biases. So I think I know why, but let me just do this. Okay, it's training again. Zeros. All right. So actually in the perceptron, what you do is you also multiply this by the X value. This is not something that you do in, otherwise I have some error if this doesn't work. So I'll have to trace it. But part of the definition of the perceptron is that you give it the actual sample again. So here I'm going to give it XI. See that? because this is not using stochastic gradient descent to learn the weights. Okay, it kind of highlights some of the problems. So let's see if this fixes it. Otherwise, we'll have to look. There's values now. You see that? So, okay. Now I did change that learning rate, didn't I? I think I changed it to a big value. Now let's try another learning rate. You see these values look pretty big, right? Actually, before I change it, let's see how it predicts. Why not, right? So how can we do that? So I'm here, right? So what do I have right now? I have a model that went, let's start there, that went from weights of zeros and bias of zero to that, whatever that means. That's what the model learned. I don't know if it's good or bad, right? How do we know if it's good or bad? We need to compare it to the X test data. Do you guys see that? So let's take a look. So before I start making those changes, so I'm going to go over here. So here then I would take the weights and biases that I just learned, right? And I would predict. Okay, ypred is predicted. I haven't done the accuracy function, but we probably should do that. Let's see what ypred has. A lot of ones, some zeros. You agree that this is the predictions, right? So at least it's predicting. But is it predicting correctly? Right? So that's the next thing that we want to do. So how can we do that? Let's look at y-test. So what do you guys think? Is it predicting well or badly? Badly, right? It's predicting badly. So we have to tweak it. Do you guys think that maybe we can fix it? Yeah, maybe. All right, so what's one handy function we should probably have is the accuracy function, right? So let's define this one because at this point we kind of need it. So I'm going to do y true, comma, ypred. So it takes accuracy. We had done this before, so I'll just kind of quickly go. np.sum. And then we're going to do y true equal ypred. And then I'm going to divide this by the length of y true. Right. So now that we have this function, we can also predict an accuracy, right? So in this, the accuracy may not be so great. Let's try it. 46. So we could probably do better than that, right? So what do you guys suggest? Well, what might be the problem? Learning rate is a possible problem. Now I've implemented, I believe, everything correctly in the Perceptron architecture, including that xi, and if this component here that I'm not so familiar with because it's not usually done in gradient descent, right? But let's try it now without the x's. Let's just see the effect. Okay, activation, predict, accuracy, got our data. I'm gonna split it, fit, I'm gonna learn. Good thing it learns fast. Okay. There's zeros again. So definitely it doesn't like the fact that it's just that little update, right? So we need to have the X value in there. Okay, so we're going to add it back. It's learning. All right, so we've got values again. It is predicting ones and zeros. So that actually is good, right? Like the values are not anything else. Okay, predict the accuracy. Okay. What else can I try? What do you guys think? This will happen to you all the time in neural networks. Yeah.
I mean, you could do the slower learning rate, like
a smaller learning rate, right? So this might be too big. I don't know. So let's try 0.01. Let's just see if something happens. Okay. See the weights and the biases. They went down a little bit, right? Did you guys notice that there's a bit of a change? So let's see. I see about the same number of zeros, actually. Still 46, right? How about an even smaller learning rate then? It's about the same. 46, okay. What am I doing? Let's do something. Let me print. It compares Y train. Did we print what's in these? Let me look at these values. All right, so I'm going to print all of these. X train. X test. Y train. And Y test. Okay, so let's do X train. It's like data. X test. Okay. Y train. Zeros and ones. Zeros and ones. Do you guys see anything? You guys see any?
Oh, I have a question.
Yeah, go ahead.
So we're running through a defined number of iterations, right? So we are not stopping when the error is the lowest, but just going until. I'm basically saying 1,000 epochs should be enough for this problem. So I'm not actually continuing until you certainly could, but I'm not doing that because the problem is the model may not be great currently. And so it could just be there doing that forever. You know what I'm saying? Like you can do that when you're sure your model is good. But right now I feel I have a bug somewhere. And so if I did that, what's going to happen? It could go into an infinite loop and it's actually not learning. You know what I'm saying? Yeah.
Yeah. So I'm thinking there's something here. But I feel the values are correct. Zeros and ones, zeros and ones. Use and
plus bias to probably people that we had not XI.
Yeah.
Plus bias.
Yes.
Okay, we had that.
We have this, and then this goes through the activation. The activation was correct, I think. It just because it produces either ones or zeros, and the model has ones and zeros, so it should produce ones and zeros. Yeah.
It's definitely not learning. When you make them float, does it improve the accuracy?
When you flip their position,
Oh, when you flip their,
you have Y predicting my flight train, it's supposed to be Y train.
shouldn't matter, I think, but
I did 63%.
you got it to go up? Well, that's okay. I think I have a thing and I'm gonna add this thing I have here in my code that forces the numbers to be 0 and 1, but they're already 0 and 1. Okay, so I have this in here. Really? You too?
It's because in your accuracy functions are flipped. And then the way, when you're inputting them, you're flipping them again. So if you look at your accuracy function, you have, Y true and then Y thread, but then when you input them, you put Y thread first.
But yeah, I mean, I don't think, I mean, if I had like put in the same one, I'd understand why. It's interesting that you guys got 100% already. That's good. I'm glad.
Update function. Looking at the real value, it's subtracting and predicting that.
Yeah, so you're saying I'm not being consistent.
I don't know if it's not consistent. I think it's just the update function. This should be flipped. And then once I added the plus Y, instead I for some reason was missing. I don't know.
That's good. Okay. Yeah, I'm processing. So I'm not saying you're wrong. I'm definitely processing. So let's see. You're saying that you just, yeah, in my code I have it flipped too. I think I mean, usually we square this anyway, so it's not an issue, but I just don't see why this would make such a big. Are we? Well, the idea is just to take the, yeah, so.
Adding currently say that when we train is bigger than one French to the base or moving away.
But it usually this is a 1 and this is a whatever the other thing is. So if it's 1 and if they're correct, right, it's 1 and 1. So 1 minus 1 is 0. But if they were incorrect, then it would be 0 and 1, which means it's minus 1. Or 1 minus 0, which is 1. Or 0 and 0, which is 0. So it really, there's just those 4 options. And sometimes it goes negative, sometimes it goes positive. It might matter. I mean, obviously, apparently it does matter. So I just think if this is a 0 and this is a 1, it's minus 1. If this is a 1 and this is a 0, it's plus 1. Yeah, so let's try it. I mean, if you all flip it and it works, that's fine. I mean, that's fine. To me, it just, but let's do it. All right, so let's do that. Oh, I was writing something, so let me put a comment here. Because I was just gonna do this, but because I have it in my code, but actually that value just makes it 0 and 1 for sure. Let's try it again. See what the weights and the biases look. They're better. And I think you guys, yeah, you got it. So 1. Good. So what does that tell you? So it does matter, right? So we're gonna have to, I guess, think about this one. What we can do is print these out, right, as we're doing it. I'm gonna print this. And I'm gonna say train minus spread. Right, and then we're gonna print that. We're gonna say minus. And we're gonna say y pred. And let's just do an input here. You guys see what I'm doing? See any errors? So I'm just trying to print this so that we can see the, maybe see the effect. Need this. Okay. 0 minus 1. So what does that mean? The train was 0. The spread was 1. 0 minus 1 would give you -1. We multiply that times the learning rate, right? That would be minus 0.01, and we update the weights accordingly. This one would be 1 minus 0 plus 1 multiplied times the learning rate, we get plus 0.001. This one means what? It's there we're accurate. So 0 minus 0 is 0. What happens? No update, right? Do you agree? This one, 1 minus 0, 1. So plus to the weights, the learning rate. Again, this one is 0, no update to the weight. No update to the weights. No update to the weights. Positive update. Positive update. No update. No update. Oh, and this is with the correct way that we had it also. So I'm going to have to switch it back to the way. Just trying to find one that is negative. If you see one, let me know. No negatives, right? Oh, there we go. Yeah. All right, great. So it is work. This is fine, right? This is the way that it should work. And you can see, so in conclusion, what is happening in essence? What do you get? You get a sign, right? That it's either positive or negative, and that is multiplied times the learning rate, and that updates the weights. And we have this X value also, which I don't like. But so I'm going to take that away. I just want to see what happens without it, but it's a thing that's in there. All right, guys? Any questions so far? This is really important, actually, because the perceptron gives you this minus plus, but actually this methodology does not work for like deep learning, but we still need this minus plus. This is where stochastic gradient descent comes in, which is a methodology for basically getting that minus plus. That's it. You see what I'm saying, guys? This thing we're getting here like this from the perceptron, but this is only the perceptron. Stochastic gradient descent, what we actually use for deep learning and higher neural networks have a better approach. And that better approach still, though, needs to give you that plus minus to do the update. Any questions? Okay, so I'm gonna stop it. I want to go back to the code, and I just want to look at a couple of things. So this was the right thing. Let's take out the X. Well, actually, let's not do that right now. How did we have it? We have Y, we had Y pred minus Y, right? So let's switch it back. It's gonna be Y pred, comma. Here. Yeah, like this, right? So let's just see what happens here. Why was this not learning? Oh, I forgot to change that order. So this should be pred minus train. Pred minus train. And then we have Y pred minus train, right? So this is the, okay. Clear the kernel. Okay, let's run it again. One minus zero, this is pred minus train. One minus zero is one. So it's positive. One minus one is zero, no update. One minus zero, no update. One minus one, zero, zero. One minus zero. So we need to, so it's currently it's only going up. Did you find, oh, no, yeah, there it is. So it does have a minus one, right? Zero minus one. That would mean it's got a negative in there. So that's why I thought both, either one should have worked, right?
Maybe if you change the, what you visualize the weights to, it'll work.
Would it change if we determine the learning rate to be a negative number? Then it wouldn't go the other direction. Would that be the same as?
Maybe. I see what you're saying. So yeah, so you're saying it goes in one direction if we change the learning rate to negative, or the equivalent of that is just doing this. This. So now it should not work in the other direction, but should work in this. Probably that's probably it. So the sign is very important. Okay, so let me go. Remove this input. So I think this will learn. Well, I think that's probably it. So let's go over here. I'm gonna clear the kernel. Okay. Weights and biases look about the same, right? As when it did a good job. Looks good. 1%. So that's it, right? So in this one, we're not squaring the differences, right? So because we are not, that's the conclusion. We're not squaring the differences, but instead we just keep them as they are. So depending on how I place these symbols, I need to know how to do a plus or a minus update. Do you guys see? That's the perceptron. That's the clever. Yeah. Do you see something else?
No, I'm asking, do you?
The learning rate. You want to see the loss? You want the loss of this. So the loss of this would be, you want to minimize the error. So print it. So we want to print that value, this one,
Yes,
because it's going to be pretty big initially, right? And as we get closer, it should be a smaller difference.
yes.
Mm-hmm.
Taking it now, we move down to the lowest point, but taking that my negative sign and putting in a positive one. And the
So we were, yeah, so yeah. Yeah, I see what you're saying. We can start here, I guess. We could also, or we could build. So we could, let's call it loss, right? And we're just gonna say this like this, and then we're gonna create a list here. Some list of losses. And then we're gonna append this value to it. That's basically what you do. And so now we're gonna, when we calculate it, list losses dot append loss itself. And then we have list of losses, so we need to plot that. So should have this, I think. Okay. And then we need, once we have that list, that's going to be the Y values. We need the X values, which are the iteration of it, right? So we need to create. Hmm? Hmm? For every epoch? For every epoch, you mean? Okay. Yeah, that makes sense. So just for epochs then, right? Okay, so to do that, then I need to average this one every epoch and add it into some other list.
Yeah.
List epochs loss. This will only have 1,000, so at least it's easier. All right. So this should be at the end of the second loop. Dot append. And now from this one, we need the average, correct? So that's gonna be what? Mean maybe, or NP? I don't know, that this is not sum it and divide it, yeah. So sum. Right, that's true. So we're gonna do average equals sum, right? List losses divided by len of list losses, right? See any errors? All right, so let's just add average here, right? That should do it. So then we have list epochs loss, and then we're gonna plot it down here. So I need X vals NP.A range 1,000. X vals. Got 1,000 values in there. And then list losses. I think we can just give that as a list. All right, so then we're gonna do PLT dot vals, comma, thousand list epochs. You guys see what I'm doing? Do you see any errors? If you see any errors right now, find the errors, okay? So I don't know if I'm remembering here. All right, so now let's run it. Let's clean up the kernel. And then we can test that. Okay. So run. Okay. Run. Data shapes. Slower because we're doing that operation. It did.
It worked.
Yeah, it worked. So no errors so far. So that means we should probably have the lists. That's during the training, which is correct. We want to see it during training. Okay. Just use so one. There we go. What do you guys see? So this is the loss. Look at that. So it's going from negative to 0. Do you see this? This is the average. Going from negative to 0. What we usually see is the loss going down, right? So is this not what you expected to see?
No.
It wasn't your theory? Okay, yeah.
But what was it?
It's going up from, yeah, it's going from negative to 0. So we usually, huh? This is the perceptron, okay? This is not deep. It's great. This actually turned out to be a really great exercise. It's not because what you will see is that we would actually square the differences to avoid these crazy things. You see what I'm saying? If you square differences, what happens? You get rid of sign. You just get difference. So if this is and this, right, that's a bigger difference than these two. So we square it. Otherwise, look at what's happening here. But then the problem is if we square it, we've lost the sign. Do you guys understand that? And then how do we get the sign? That's basically literally why stochastic gradient descent was invented. How do we get this sign? Okay, but this is interesting. So, all right, so this was your idea. So,
We put a negative sign all the way to the top in the predict or like weights minus.
wait, hold on. Where in the code?
Weights minus.
Oh, yes. Yeah. So change this, the plus, right? And was this the right approach? Was this the right ordering? Okay, so this should be the correct way, is what I'm saying.
If you have pluses there, you want to put like red.
Yeah.
Okay, so if
But
I,
that's the other way.
yeah, I see what you're saying. So if I have what Y pred and Y train, I want to have pluses here. Minuses. Ah, okay. Yeah, and if I have Y train, Y pred, then I want to have pluses. Okay. So then I have Y pred, Y train right now. So I should have, so then this won't learn them.
Yeah,
Oh, you want to see when it doesn't learn? Ah, I understand. Okay. All right. So everyone with me? With us? All right. So let's see. I'm gonna again clear the kernel. Learning, this is where it doesn't learn, I believe. Yeah, this is bad numbers. So let's see what, this is where the graph will be what you expected probably.
It's not learning. It's learning. Not learning.
In the wrong direction. Right?
It's unlearning.
It's unlearning. That's interesting. So it's predicting a lot of ones, maybe. Right? Oh, 46 again.
And getting them dead with another. Oh, I guess, yeah.
It doesn't learn. It just, that's what that tells me, because this is, well, it's the average, right? But it's that average of all, and then it's always actually pretty similar to the actors. This is what you, huh?
Very interesting.
Yeah, very interesting, right? Anyway, so as you can see, the Perceptron definitely works, but it's got some weird behavior, right? Do you guys see that? Okay, so let's now go back to, do you guys want to see something else, or you're good? Yeah, go ahead.
Never would we use Perceptron in real world.
Never.
Okay.
Never. So that's what I'm getting at. So this is the start of it, but really we use stochastic gradient descent, which is actually almost exactly like this, except two things, obviously. One is this symbol thing, it's not a thing. So what, you can solve this because you do want the difference, right? But you don't want the sign. So you solve this by doing something like that. That gets rid of the sign. Do you guys agree? Okay, great. This symbol, although this is dependent on the loss function, right? But you can understand the concept. This symbol, by convention, is always negative. You don't have to worry about it. The learning rate is always negative. But then you do have a problem. You have the problem of how do you, the update is still the learning rate, right? So that you don't have this X either, right? The learning rate, you do still have that. But then the challenge that we're left with is, how do we get the sign, plus or minus? Do you guys understand that concept? Anyone know how we solve that? Calculus. Right, so calculus solves it, right? Because, and this is what we're going to look at this, but basically using techniques from calculus, we look at that function and we can estimate what is called the slope of something on the function, okay? We'll get to that. Obviously, do we have to calculate that? No, TensorFlow and PyTorch do it for you. But this actually turned out to be really nice because that symbol thing that we are trying to estimate is really what we're searching, okay? And so that's kind of what I'm going to get into. We have a few minutes left. So we will talk about how stochastic gradient descent kind of does that, right? But the idea is that this, would you say, like if this was regression, it would be like that, right? When we minimize in linear regression from your stats class, what did you learn? You take the difference between two values and square them, correct? So that's this. Do you agree that this is also a function? This is a function. We will explore this. It's called a quadratic function. We will look at these things, and then we will learn that given a function and the values, you do a procedure called taking a partial derivative, right? And that at that point, then we know
we get a little value, basically, that tells us what is something called the slope, and that basically gives you the sign. That's it. I mean, that's literally what it is. So here, what's missing, imagine this, in the 1940s, they created the perceptron, and all was needed here was something called, let's say, calculate gradients. That's all that was missing. Okay, these gradients would then give you the value that would allow you to set the plus or the minus. Does that make sense? All right, so that's important. So let's do this. Let's fit. So I think the perceptron is clear, right? And it serves as a good stepping stone to understand the next set of algorithms. So we'll do a couple where we actually literally put in the gradients in there, right? So that means that now, how can you get, let's say that you have, so what I'm saying is we're going to take a function and do a calculus operation called taking a derivative. That's like a operation. If you know calculus, right, you take, there's like rules. What's the derivative of that? 2x. So if you have x2, it becomes 2x. Why do you know this? Because you like have to memorize this, right? So it's basically like that, okay? But what we know is that we could have a function that gives you that, right? You see that? So in some of the examples, what we will end up doing is we will just assume some function and then assume its equivalent so-called derivative and hard code it here. You see that, guys? And then if you hard code it there, you have the value. However, that wouldn't be practical, right? So instead, you need to calculate that via the code. And that's where TensorFlow is literally what it does. NumPy can't do this. Okay, NumPy does not do this gradient calculation. But I think it's motivated now enough, right? So we have about 8 minutes. So let me just, if I'm not hearing any questions, right, you kind of understand where we're going and what we're missing. Let's just finish Perceptron to make sure it works, unless you want to see anything else. You want to see anything else of it? Nope. All right, so let's just help me out to get it to the right stage. So, I mean, so what was it? So y pred, y train. So then these should be negative, right? Yes. All right. So we're good. Yeah. All right. So let's go ahead. Oh yeah. Did I leave the square? Oh yeah. Okay. Yeah, because that will not let it learn, right? Right. Good. So you can see. I mean, it's funny, but I'm not kidding when I say this is it. This is the whole mechanism that all of neural networks is built upon. Everything learns like this. In a loop, trying things out, but smartly learning, right? And you have to minimize this error, which is the thing that I guess we printed, right? We printed that. All right, so let's go ahead and let's make sure it works. Let me do a clear output here. Okay. We'll run it, just make sure it works. Right, good weights, good biases. Looks right. Yeah, 100% accuracy. And there's her loss. Negative to 0. Usually we would want the other thing. All right. Yeah, so good. So it works fine. Okay, so now that completes the perceptron. As someone asked, you will never use the perceptron, right? The things that need to change is we need to get rid of the sign. Obviously, that creates some confusion. And then this is always going to be negative, but everything else stays the same. So what we need to learn here is going forward to calculate these things. All right. So now, as it turns out, for regression, for instance, what ends up happening is it's always like this minus this squared. So technically you could say you always kind of know that, right? And so you could think of generalizing an equation that's the derivative of the original one, and then you can calculate these gradients. Remember, the goal of that is to get that plus or minus. So actually this will take some time. That's this part of the lecture going forward. So I have, so since this completes the perceptron, let's just go over to the next thing that I was going to talk about today. And that's under the, if you go to the machine learning foundations repo, neural nets, and then maths, I added this already for you. This is called computing gradients. Okay. What is computing gradients? Gradients is the name given in machine learning and neural nets to this idea of these derivatives. Okay. And this process, again, even if you don't know anything, you know, let's say of calculus, you know, what is this process for? To get that plus or minus symbol, right? It gives you a value, but also that sign. So just, I guess I won't run it today because we're almost out of time, but I will kind of give you this. You can play with this over the break. Okay. So you obviously, to do this, I'm going to use TensorFlow. So as you can see, I have a function here, right? We'll cover this later. I have a function that represents, you know, that thing that we're trying to minimize. I have some data. You can plot the function, right? And then what happens here is via TensorFlow, you're going to calculate these gradients, right? And once you calculate the gradients, here they are. These would be the little values that we would plug in into our model. The thing that determines pluses or minus, because these could be plus or minus. Do you guys understand? So all I'm saying is this, we'll cover this in the next lecture, but basically to calculate those values, we would use TensorFlow itself. So take a look at this over the break, and then we'll pick up here when we return. Enjoy your spring break. Remember, no class next week. Also, please start working on your term project. So use the time to start thinking about that, right? And if you have any questions on this or anything, I'll stay for a few minutes. Otherwise, have a good rest of your day.